think we were, yeah, we were here. So we started getting into talking about the conservation of momentum, right? And I didn't quite get to make the slides to kind of go with this, but just a quick view of our momentum, right? Once again, I go through the top, right? When we talk about momentum, right, it starts us to get into talking about how in the system things are being conserved. So when we talk about being in the system and how things are conserved, right? We first talk about momentum and how we say momentum is like mass in motion. So we're thinking about like a car, things going, right? Even thinking about news, first of all, object in motion will stay in motion. So we see like an object moving has a mass and its velocity, then it has momentum, right? So then we say momentum is equal to mass times velocity. We have the units for momentum. Understanding momentum is a vector quantity. The important part of it being a vector quantity is that the direction does matter. So which way you're going actually does matter. Because now it's in a conserved system, we know that the initial momentum is equal to the final momentum. So right then and there, right, I want to stay there for a second. Momentum is a conserved system. So if I take that, right, staying with this concept, right? I feel like I'm missing something. Was that it? Let's look at that last concept and we'll talk about what that really means. What does that mean that momentum is conserved in the system, right? How does this look on camera? Move the camera or it's a scribble. I just want to know how it looks. Should I move it or change the color?
Yeah,
That's better? Okay. So really trying to focus on what does this last one mean, right? Momentum is conserved in the system. So inside, let's say my system, right? Let's say my system is like my house, right? So in my house, I say whatever comes in my house is the same thing that goes out my house. Like we're just looking at it like that. Like everything that comes in is out. So if it's 3 people in my house when we start off, leave out, it's gonna be 3 people. I'm trying to make a better analogy, but like that's the way I can say, like, look about your system as like whatever in your house, right? So if in my house, I start off with a certain quantity, I call that my initial, right? So let's say we look at momentum, right? My initial momentum is then going to be equal to my final momentum. That's what we say when we say a system is conserved, right? So like before we talked about a couple quantities, we talk about the change in momentum, which we'll get into, is equal to the final momentum minus the initial momentum. And what do we say momentum is equal to? Momentum is equal to mass times its velocity, right? Including it's a vector quantity, so it has a direction. Let me put a vector here. So, you know, vector quantities, vector quantities, vector quantities, vector quantities, vector quantities, vector quantities, right? So with me knowing this, right? Now I can start talking about how I can identify certain things in my how do I say it? In my system, right? So let's say in my house, right? It's me and Sean, right? Me and Sean are in my house. So now I have a mass, right? Let's say that's mass 1, right? Sean has a mass. That's mass 2. We're both in my house. Now let's say we're moving in my house, right? We're moving, so now we have a velocity. So now we have a velocity, right? So I have a velocity, and Sean also has a velocity. Together, we have a joint momentum between our individual momentums, right? So I'm a lot more massive than Sean, right? Obviously. So I have a certain amount of momentum. Sean has a certain amount of momentum. It's just going to be different, just solely just off of the masses. And then how fast we're moving with our velocity in the direction shows that too. But together, we have initial momentum in our house, right? In the house. Now, afterwards, we both have the same total system momentum, but it might change a little bit, right? Maybe we run into each other and we collide, right? Maybe I bump Sean outside the house, right? I don't even know, but like we just collide. Something happened, this change in momentum. So now we have this thing, maybe our mass doesn't change, but we have, let me do a different color. The velocity might change. So I put this little dash right here, the symbol a prime, right? What does that prime mean? We have a new velocity. So our masses are going to stay the same because our mass always stays the same. But now, after we collided, we have a new velocity. But with that, it's still the same total momentum. Where do we see that at? Remember these problems? If you can still see your slides, hold on. We did all this. We got into impulse, change of momentum. Second law, impulse is equal change of momentum. This one, right? So remember we did these? We had two examples. When we had the explosion before the explosion with the boat, right? He had an individual momentum of, I think it was 50, right? And then the boat had a momentum of 100. So together, their momentum together in the system is 150. So afterwards, we're expecting the momentum's total system to still be 150. But what changed? Kent jumped off and his momentum was 100, 200. But the boat's was negative 50. What does that mean? Kent jumped off the boat. His momentum was going in the same direction, a little bit more, but the boat had. Why? Because he pushed off of it. Now the boat's moving backwards. So if I jumped out of a boat, I would expect the boat to go backwards if I was on the water too. But in total, my momentum is still conserved. So that's the example we see right here. Now, this is the math behind it, right? This situation we call, this is an inelastic collision. I think I spelled it right. I might have spelled collision wrong. But this is what we call the inelastic collision, right? Still momentum is conserved, right? Momentum is still conserved, right? Still conserved. But when we have an inelastic collision, we refer to it as this right here, right? Can we give me some examples of inelastic collisions?
Cars hit each other on the street.
Stay right there. Two cars hit each other on the street. But what happens after they hit each other?
One will either be pushed or they'll stop.
So when they leave and they interact, right, there's still two individual cars, right? So like one might go this way. Like they come, right? Here's the first car. Here's the second car, right? This one's going this way. This one's going that way, right? This is before. And let's say after. Let's say one goes this way, right? And then the other one might bounce off and go this way. It doesn't always have to be like that, but is that what you're getting at?
Yeah, there will be some reaction, whether it's
Opposite, equal, whatever, right? But they still interact and they remain being individual, right? Now, you drive? Okay. Have you been in a car? Have you been on the highway, right? And have you seen cars?
Yeah.
Okay. Now, have you been in a highway and seen a really bad accident?
Yeah.
To where maybe what happens when two cars are lodged into each other. So now
it's smushed under, they
almost fuse, right? So where you see something like this, right? We have the same scenario. The two cars come in, let's say head on.
The inelastic part of the collision just means they're two separate.
Godly. Oh my gosh. Sorry. This is an elastic collision.
Elastic collision means that at the end it's two separate.
Car crash was easy, right? It's here. I'm sorry. Car crash is like the first you come, but an easier one would just be like a ball, like two billiards. They bounce right off each other. Anything with a ball is like an elastic collision because you think about it, so it bounces off like a rebound, right? Elastic, right? But I can't believe I just messed it up. I apologize. So this is an elastic collision. They interact, they collide, but they will remove each other and be separate afterwards, right? They still have their individual momentum. So now let's say we have an inelastic collision, which is basically us going now. Our two cars. They hit each other and now they're stuck.
Or if you throw clay at a wall.
Clay at a wall, yes. Now my two cars are like this. They go, boom. My two cars are stuck together, right? They might even roll a little bit. So they might hit each other and roll for a little bit long, or they might hit each other and they stop.
Momentum state, the final momentum stays the same in both inelastic and elastic.
Exactly. But how would it be different in elastic? Sorry, inelastic. The initial, I'll give you a hint, right? The initial is still the same, right? It's two individual set momentums, right? Like this is my car one, this is my car two, right? But before I go ahead and fix this part, let's think about it logically. In this one, they hit each other and they bounced off pretty much and still had the individual entities, right? What happens when they came here and they collided? They basically became one. So now they're one. So together, I was added though.
Is it an average or is it just addition?
Think about it. What now have they combined?
You counted as one object.
So now with one object, they have one
velocity
and one mass. So now I can actually represent this now as, let's say if I do this, mass one, which is my green car, and mass two, which is my red car. Those now are added together because they're joined together. And now, like I said before, when they collide, they come together, boom, and it might roll a little bit. It might stop, but they're moving together at the same velocity. So now they share a new final velocity, right? This is an inelastic collision.
And it's only getting, does it have to have that, let's say if two forces, two objects meet each other and then they just cancel. Is that inelastic or elastic?
Cancel is what? They don't move no more?
They don't move, like they crash and then they stop competing.
So now, what is their velocity?
They won't have,
So then it's just zero.
but the momentum will change.
So then it would still have to be at the very end, right? Like if they come to a complete stop, this still at the very final will still have to be the initial. So we'll still see that with the math, right? But it's just saying like it can be that at the end that they eventually come to a stop or a hot or they move, right? We will see that in this situation here, right?
So they get what you're trying to say about the system conserving itself, right?
Yes.
Things collide and then both of those things get together and then they skid or slide along with the party.
Yes. This is what I would have put in the slide, right? Only thing is like they skip over this part and kind of like do this intuitively in the book, like in the chapters. But like this is actually how I learned momentum. It's actually an equation. Breaking it down from elastic and inelastic collisions, right? So now let's think about this problem that we see right here, right? Based off of what I just said. Kent's swimming, right? He's jumping out of a boat and landing on the dock, and then the boat goes backwards. So there is a collision because he leaps off of the boat and then lands on the dock. So he's pushing off of the boat. That creates a change in momentum, and the boat goes backwards. He goes forward. What type of collision is that? Elastic or inelastic? Elastic. So if I wanted to represent them mathematically, I would use this form of momentum conserved, right? I would take his initial momentum, his initial mass and velocity, the boat's initial mass and velocity, find them, add them together, and then I use this at the very end to figure out the individual velocities. But they still have the same mass, right? But I play around with this. Or he did momentum. But both of these, like we see, will equal 150. What about the next one? Where it's the cannonball coming out of the cannon. Is that an elastic or inelastic?
Yeah.
Still elastic, right? They come out and now they have their own individual momentums at the end. But together in the system, it's still conserved. Now, what I brought that up is because we got to this point. Let me add some filler stuff, right? Change of momentum. Just so remember, is equal to mass times the change of velocity. Then we got impulse is equal to force times the change in time. And then change in momentum is equal to impulse. Just so we add all those things together, right? Just so you have that. Now let's think logically, right? Look on the slides. This problem right here. So we have a medicine ball, right? It's throwing at a velocity of 15 kilometers per hour to a skater who is at rest on ice, right? The skater catches the ball and then starts to slide with the ball across the ice. You want to consider the skater and the ball as two separate parts of an isolated system and then fill in the before and after, right? So somebody throws a ball, right? The ball is floating in the air and the skater is chilling, right? And then eventually she catches it. She catches the ball. So we're now when she catches the ball, her and the ball start going and moving on the ice. As you see with ice, it's probably like no friction or little friction to where now she's just sliding. So that gives her now some momentum going in a different direction. So we can still represent her by this as in the ball as two separate objects, right? So I do it like this. It's probably easier for me, but I'll do it like with the equations. I'll do them blue. I'll just pick blue. So let's say we got M1, which is the mass of the ball, and that has its own velocity. Or I can do it like this: mass, ball velocity, plus the mass of the skater and the skater's velocity, right? And let's just start there. Before we get into the final, let's think about it. You throw the ball and you catch it. And now what you catching it, you're sliding with the ball. You throw the ball and you catch it. Now afterwards, you're sliding with the ball. So if you're sliding with the ball, what can you say about you and the ball? You're one. So now what you won, how does that represent what's representing you with your mass? Your mass will increase because now you have a what? A addition of the ball. So I should do what with your masses? I should add them together. Now with me adding masses together, because you're one, would you guys have different velocities or the same velocities afterwards? You would have the masses added together and you would have the same velocity. By thinking about that type of interaction after a collision, what type of collision would you classify that as? Elastic or inelastic?
Wait, for the ball.
If I catch the ball
And you move in a direction because
with the ball, as in you just threw me, throw that marker to me. I caught it, and immediately as golly, that was terrible. Immediately as I caught it, right? I caught it, I start going backwards this way.
Yeah.
What did I just add? Throw it again. One more time. Throw it. And now I start going backwards. What did I add to me? What did I add? Because I added a what? An object that has. So now I got, let's say this is 2 kilograms. I got 2 kilograms more on me, and I'm going. But did I drop the 2 kilograms? No, it's with me, right? So now this 2 kilograms plus me is going this way. So now we're going together. So now based off of both of these, which one are we? So it's an inelastic collision, right? So now I know afterwards, let me change the color. I should be representing this as both of these masses of the ball and the mass of the skater together, because now they're going to come out with the same velocity, right? This is for this problem right here. Now we know the mass of them, and we can actually put these together. So before, what is the momentum of the ball? First, the ball has what mass? What's the mass of the ball? Just tell me the number. Anybody?
10.
10 kilograms. All right. What does it say about the ball? It's traveling how fast? 15. We'll just say 15 kilometers per hour, but we'll just say 15 for right now, right? So we can calculate this individual momentum of the ball, right? It's the mass of the ball times the velocity, which is 10 times 15. What is 10 times 15? 150. So the initial momentum of the ball is 150 kilometers per second. That's a weird unit, right? But we know that it's 150 for the ball. So we put that in the top left. So now we know that's 150 because we just figured it out. Now, with the skater, right? What's the mass of the skater? 50, right? Did they give us a velocity for the skater? Technically, the answer is what? Why is it 0?
That's you said, right? So
So that's what we're assuming, right? We're assuming because it says that she's at rest. At rest would mean that she has a velocity equal to 0, because at rest would mean like what I'm doing right now, just standing. So now that we say that her velocity is at 0, her mass is 50, her velocity is 0. So when I want to find her momentum, I do 50 times 0. What is 50 times 0? 0. So it means that she has no momentum. Does that make sense logically with what we see in the system? If she's at rest, would she be moving? No, she wouldn't. Sorry, let me not say she would be moving. If she's at rest, would she have any momentum? She wouldn't have any momentum. She's just at rest. She's standing there waiting for the ball to be thrown to her. So now her initial momentum is 0. Now, what does that say altogether about our initial momentum in the part of our system, right? It's the momentum of the ball plus the momentum of the skater. Now we have them both in the same units, so we can combine them together to find our total momentum in the system, right? So all I have to do is add 150 plus 0. What's 150 plus 0? 150. So my total momentum in the system beforehand is 150. So that's what we put now in this last one, where it says total is 150. So now the way it goes is kind of like a circle with this problem. Do it like a circle, right? Now that we know that this is 150, we know that momentum is conserved, right? So the initial momentum is going to be equal to the final momentum. So now we just found the total momentum for initially is 150. So what should the final momentum be, the total? So it should be 150. So we can fill that down the table. Did someone just say something?
Yeah, I'm just trying to figure out, is there any way I can make my screen bigger? Because sometimes the lights from the classroom is hard for me to see. So I click full screen in the pen, but it's still not making it bigger.
I actually don't know about that. All I could do is try and move this board. Hold on. Is that better? Did that help out?
Yeah.
Okay. So now we here, if you look at, where is it? This part, I just kind of did it. So this was 150, right? Now, because we know this is 150, we know, I didn't mean to press dictionary. This is 152. But how do we establish what type of collision is this? Inelastic or elastic? Inelastic or elastic collision? What is it? Inelastic. So we know that the masses are going to eventually be joined together and they're going to share the same mass, right? So now, let's think about it, right? We could actually find out these ones together. What is the mass of the ball? 10. What is the mass of the skater? 50. And they both have the same velocity. Now, I could add these together, right? Pretty much. And then it'd just be 60 kilograms times V. And then I'll be able to know that this is equal to 150. And then I could just do 60 divided by 150 divided by 60 final velocity, right? But that's not really what the question is asking. They want you to represent their actual momentum based off of just that velocity. We don't have to find it, right? So let's think about it, right? They both share the same velocity. Taking you back to 7th grade, maybe 8th grade. When we get to factoring, right? I want to represent these both the same way like this, individual momentums. So what I'm going to do is factor this here. Sorry, I'm saying the wrong word. Distribute the velocity to each individual mass. So what does that really mean? I do 10 times the velocity and 50 times the velocity. Right? So now I have my new momentum of the ball and my new momentum of the skater. So technically, what's my momentum of the skater in the final? It would be 50 times the final velocity, which is going to be here. It's going to be the same thing. 50 times the final velocity. And my ball has momentum of 10 times the final velocity. The same thing here. Now we have them joined together to where now we can look at them as, okay, here's my initial momentum and my final momentum. So in the chart, right, for the skater, you will put 50 times the final velocity. And then the top part, for the ball, you do 10 times the final velocity. See you later. Right? Now, I'm saying it online, but I'll write it here and I'll write it on the board. So now this would be 10 times V, and this is 50 times V, right? Now, the last thing that they're asking is the change in momentum, right? So now that we have all of these, right? For my change of momentum, I'm going to do it in green, right? So where I want to pair them together. Actually, yeah, I'll do one for the ball, and then one for the skater, and then we'll do one for the total, right? So in each scenario, you got to find the final, and take it from the initial. Final from the initial. Final from the initial. But in 3 different scenarios, right? One for the ball, one for the skater, and then one for the total, right? I am leaning in my brain, but follow me. Now, here's my math, right? All I'm going to do is just take my green marker and I'm going to find my initial and my final so I can subtract them, right? So for the first one, right, I'm looking for the ball. What's my initial for the ball? Initial momentum right here, 150. I put the B under it, but when I first did it, but I also found it because I did 10 times 15. Because the mass was 10 kilograms and the speed was 50. That was when we first started, 15, we started. So I found that one, right? Let me see if I can find what its final is, right? Here's another B1 that I put right here because it still has the same mass, but it has a final velocity that we didn't find. We didn't have to find it, but we just represented it. So now I have this, right? So the change in momentum would be my final 10 minus the final times the final velocity minus my initial. Final minus my initial. 10 times the final velocity minus my initial, which is 150. So that's all we put for the change in momentum for the ball, right? And we do the same thing for the skater, right? So let me find the skater. What was the initial for the skater? It was actually 0. I put the S there, but why was it 0? Because she was at rest. So we had initial momentum is 0 because she was at rest. Now the next thing I want to do is find my final for the skater. It's right here. 50 times the final velocity. So now I have my final, which is 50 times the final velocity, minus 0. 50 minus final velocity minus 0, right? Which is basically just 50 times the final velocity. That's my change momentum, right? Now let's do the last one with the total, right? Now, what did we say earlier? We said momentum in the system is what? C word. Con. Read that last sentence. Momentum in a system is what? Momentum is conserved. Conserved in the system, which means that my initial momentum is equal to my final momentum. Now, if I say my initial momentum is equal to my final momentum, what would you expect my total change in momentum to be between my initial and my final momentum if it's conserved, which means they're equal to each other? If my left is equal to my right and I subtract them, I should be left with, or yes, 0, or it just in logic. If I have my left and my right, they're both equal, and I just subtract them, I'm left with nothing, right? So I should expect it to be nothing. 0, yes, is 0, but that's math. Think logically. I have the same in my left, I have the same in my right, and I subtract them or throw them away, I should be left with nothing. So let me look and see if I'm left with nothing. What is my initial total momentum? We said it. It was 150. What was my final total momentum? 150. I said my left is equal to my right. I subtract it, I should be left with nothing. What is 150 minus 150? 150 minus 150?
0.
0. So I'm left with nothing. This is good because it means that my system is conserved. So at the very end, yes, when we fill in the table, we have those results right there, right? Pretty much the same thing we had before. Now, with this, right, we can actually find this because it ends up being 150 equals 10V plus 50V, which is 60V, is 150. Trying to think. What's 150 divided by? That's like 60.
2.5.
2.5? So the velocity afterwards is 2.5 kilometers per hour. So you can find the total velocity that they're doing right here. It didn't ask for that, but we can see that, we can find it. But that's what we use momentum for. Because after you collide, you want to see how fast they will actually go, right? That's what you want to see, but you can find that easily. But to find that, you actually have to use what we know about the different type of collisions to make sure we put everything in the right place at the very end. Now, this is a lot on the board because I mixed it in with some pre-stuff to teach you it. But the math part, don't get caught up in the numbers. It just tells a story. This change in momentum being 0, just shows that my system is conserved. By me knowing that my system is conserved, I can find the momentum of individually to change how momentum changes between the ball and the skater. By doing that, I can represent them now in a system of equations to where now I can find out the unknown quantity, which is their speed at the very end. So that's all we're doing this for, to really understand how a situation is happening in real time. And we can do that by looking at the situation by understanding momentum is conserved. Now, where this is useful at, anybody think about like the inelastic, elastic collisions, right? When like cars are being like tested, so like for safety. So like you're driving on it, like they do the like the commercials where they have the dummy in the car and they have it just ram and just go up first. Like that's a collision, right? So they might put different forces, go at different speeds, and they want to analyze what happens to the person and or the dummy at the collision, how much force that they're getting. So now when they know, okay, is this car able to sustain this amount of force? We calculate it to be this. Does it match up? And we test it, just like how we have to do labs, right? Then we calculate to where we see, okay, what happens? This person hits this thing, they have the head jerk. Okay, they won't be able to sustain this amount of force. The dummy breaks. Like that's where this type of evaluation stuff comes. It's going to be with higher force. It's going to be with a little bit more staunch numbers, but it's really the foundation is just understanding, is it inelastic or elastic collision? What's the mass of the dummy? What's the mass of the car? Do I have a change in momentum or an impulse, which is a great change in my force applied over time, to where now I'm going to see change momentum to where I have to see if this person moves at a higher velocity and can handle that force. So that's a real world application of understanding condition analysis. So this is the same thing right here, right? So this one actually is a car. So we'll be doing this one with a car, right? Let's try and talk through this as best as possible. Actually, yeah, I'll do that. So now we have a truck, right? 48 kilometers traveling with a velocity of positive 4. So just say positive is going to like the forward direction, right? It collides head on with a 12 kilometer car traveling with a negative velocity of 12 meters per second, right? The truck and the car entangle and move together after the collision. So I got, like I said, my big truck and my car. One is moving. Oh, so it makes sense. Truck, car. Truck's going this way, car's going this way. Boom. They entangle. So now when they entangle, they move together. And we want to see how they move together, right? Do they go this way? Do they go this way? We can actually figure it out from the math, right? But first things first. Truck, car, boom, entangle, and they move together. What type of collision do we think that is? Elastic or inelastic? Say it louder. Good, inelastic. So now that we know we have an inelastic collision, right? What does that mean for, let's say, how I should think my math should look? I have individual car, individual truck, but at the end they come together. So now I have individual mass, but together they come and I have a joint mass. So now I have a joint mass and they move. It says it in the problem. They move together in this entangled fashion. So now not only are their masses put together, they're going to move at the same velocity. So I know that everything should look like this. But what's going to change? First, my objects, right? Now it's just car one. No, truck. Actually, let's do truck and car. That's all that's really changing. Got a truck and a car. Still same type of collision, right? But now numbers are just a little bit different, right? What's the mass of the truck? Compared to a ball, it's pretty big. The mass of the truck is how much? 4,800, right? And it has a different speed. Instead of 15, what is the mass of the speed of the truck? How fast is it going? 4. And the thing that's important is it's going forward positive. We'll say it's going forward like to the right, right? So positive 4. We just want to keep that so we know the direction. And we got a car, right? What's the mass of the car? What's the mass of the car? 1,200. Good. And it's moving with a velocity. What's that velocity? -12, which means, like I said before, truck, car, truck's going this way. This is the positive direction. Car is going this way. Then they collide. Boom, boom, and they stuck. Now we're at the tangle part, right? So this one's going the opposite direction and it meets head on, right? Before we come back over here, I can actually calculate these individual momentums. So I could do 4,800 times 4. I think I could do that in my head, right? What is that? That'd be 96. So that should be 128. And what, 2 zeros? Oh, I was close. Not 128. What is that? 1900, 200. Yeah, because it's 96 times 2. Yeah. 1900, 200 kilogram meters per second. So that's the momentum there. I just did 4,800 times 4. That's all it is. But I can find that one, right? And I can find the momentum initially of the car. So it's 1,200 times 12. So that should be 144, and just add 2 zeros. So that should be 14,400, right? Yep. But what's important is the direction, right? It's negative. So technically, when I add these together, I basically subtract them because one's going, one more time, truck's going this way, car's going this way, boom. So now I can get here and I can actually find my total momentum. Add them together, which is really kind of like subtracting. So I got 19,200 plus a negative 14,400. In total, I'm just looking at the answer, yes. Because I just don't feel like doing the math. But you get about 4,800. This is only by adding the negative to the positive, or you can say subtract. So these two together. Now, why does it make sense? One more time. Big truck going this way. Little car coming this way. Boom. That's their initial together. Right here. Now we're at the point here where they both collide and they're moving together. This number is positive. Remember, we said momentum is a vector quantity. So with this number being positive, we can assume that the direction is also positive. What does that mean in the situation? That means that once they go, boom, they go in the same direction of the truck. The truck's the bigger object. And once it hits with the smaller car, it carries that, pretty much carries the car with it. So we're now, if the car was going this way, the truck is going this way. When they collide, they keep going this way forward in the direction of the truck. Now, if I was to see that accident happen in real time, I wouldn't be surprised. I would expect the truck to take the car with it. So now they're entangled and they're moving along this way. So now that we know that momentum is conserved, so we can actually say that we expect the momentum to be the same of 4,800 in the positive direction. So now with it being 4,800 in the positive direction, now we come here and we can kind of break all these apart one more time. All I got to do is take the mass. What was my initial mass for my car? 4,800. What was my initial mass for my car? Sorry, my truck. My truck was 4,800, but my initial mass for my car was 1,200. So now I have us together. Can I add them together and then just go to like a final velocity? Yes, but we want to represent them in quantities so we can see the initial minus the final. So what I'm going to do is distribute my final velocity one more time. So where now I have the mass of my truck times my final velocity plus the mass of my car times my final velocity. So that's what I have right there for those two. Now I come back down again and I already have them identified for my change in momentum, right? For each individual one. So my total, but then you got my car and my truck. I want to do the same thing. So let's start with the truck. What was my initial for the truck? 19,200, right? What's my final? I have truck, 4,800 times my final velocity. So I have my change momentum is really my final minus my initial. So I have 4,800 times my final velocity, which is my final momentum, minus my initial momentum, which was 19,200. So I can do the same thing for my car, right? Let me find my car. Here's the one for my car. And here, this is my initial. Here's my final, initial. So when I come here, right, I'm looking for my car. Where was my initial? Negative 14,400. Now that's important to make sure I keep the negative because the direction does matter, right? And then what was my final, right? My final is 1,200 times the final velocity because they both have the same velocity, right? So when I take these, I have this one and then this one. You just leave it like that. I gotta change it, right? Now, when we look at the total change of momentum is conserved. I have something in my left, and it's the same as something in my right. If I take them away, I should have nothing. So we're expecting this to be 0 at the very end. Now we got here, and what is my initial total? 4,800. What is my final? 4,800. So by doing this, 4,800 minus 4,800, we got it to be 0. So everything matches up, right? All you just do is the same thing we did before and just fill in the table for all those quantities. Don't quit because you see the math. The explanation is there too. What you really want to do is start here. Make sure you start here. Figure out this is true. Now you got to figure out if you use 1 or 2. Once you get here, then you start playing around with math. Because if they bounce off of them, you don't use 2. If they bounce off, you would use 1. And now you just do a whole different thing. The initial part is going to be the same, but then the final is what changes. So you start here, then you plug in some numbers. Because even in this question, right, they didn't ask you to calculate the final speed. They just wanted you to represent it. If you can understand this with the letters, then doing the problems later on where you actually have to calculate it should be pretty easy to do. How does this one work? All right. So now we're going to work on, I believe these are perfect. Yes. All right. All right. I'm going to put y'all in breakout rooms, and I want y'all to play around and try and do these problems right here. Give me 1 second. And it'll be a mix between how many do we have? We have, so if I did 4, how does it work? Let's do, I might have to just do 3. Wait, let me do it like this. Hold on. All right, okay. So let's do this together, right? I'm gonna do, before I put you in breakouts, I have it ready, right? But let's do this together. Actually, no. I want you to go to breakout rooms and try out the one that I assign you. So I want, in the thing it'll say A, B, or C, and I want you to try out A, B, or C, and then we'll do D, E, and F together. So I don't care if it's wrong. I don't care if you struggle. I just want you to come up and just try an answer. Peter, work with Kimberly and Lakshmi. They're online, so you can see like their thing. But everybody else has it. Anna and Cindy, y'all working together, and the room should be open now. Courtney, Izeli, and okay, she's driving. And what you call it? Seth. All right, room's open. Go ahead. And it has which one you're working on in the top. So let's come back in about, let's say, 5 minutes.
Hey, I have a question.
Yes, go ahead.
My group was kind of trying to figure out what question we're supposed to be doing. You're talking a little fast. Are we doing
B.
some B? Okay.
Yeah, B. Also, be safe because you are driving. All right, how I want to do this first, I want, if it's possible, for group 2, which was I think Seth and Courtney, can you share your solution and just really kind of talk through it because you are online? I'm gonna let the other 2 groups, because they are in person, get on the board. So I just want you guys to just kind of talk through your solution first, if you can.
Do you call out B, our group?
Yeah, B. Just talk through it.
So yeah, we use the equation initial mass and velocity 1 plus initial mass and velocity 2 equal to final mass and velocity 1 plus final mass and velocity 2. Since we're finding the final velocity, it would give us the equation of final velocity equal first mass time first initial velocity plus second mass time second initial velocity over mass 1 plus mass 2. That would give us 18 plus 40 over 13. So it's 58 over 13. That would give us about 4.46, if I'm not wrong, meters per second.
You got the right answer. Yes, that's good. Now, 2 questions I'm gonna ask you, right? Just so we understand, right?
Mhm.
What type of collision is this? Is this an inelastic or elastic collision?
Can you repeat it?
Is this an inelastic collision or elastic collision?
I'm assuming elastic.
Now think about it, right? Elastic. Think about like a ball. We say a ball has elasticity, right? So what happens when you throw a ball against the wall? It does what?
It collide.
Say it again.
It collide.
It collides, but like, how does it collide? Does it stick to the wall? If it's like a bouncy ball, what does it do?
It'll bounce off.
It'll bounce off, right? So when we think about elastic collisions, we think about it bouncing off. Now look at the picture for B, right?
Oh, so it's in elastic since only one ball is moving.
Only one. Well, technically, you got the ball. What happens with the 2? You got 2 individual balls, right? 2 objects, right? What happens afterwards? Do they stick together or they bounce off?
It bounce off.
Look at the picture.
Oh, from the picture, it sticks to itself.
So they stick together, right? So now, one more time, is that inelastic or elastic?
Inelastic.
Inelastic, right? So now what we talked about earlier with the 2 different equations, right?
Mhm.
We expect, let's not even get into the equations. Let's think about logic, right? They both are individual. They have an individual momentums at beginning, right? But when we look at them end, if they stick together, what does that mean when they stick together? They join what? Instead of it being 2 individual masses, they both have now what? The same, not the same, but they all become what? One
The best.
mass together, right? So you add those 2 masses together, so now you get 1 mass plus the other mass. So that's how you get the 13, right? And because of the masses are added together, they share the same velocity now. So that's that V prime. So all the math that you do to get there is good, right? But really understanding that full concept of they were 2 individual objects before they collided. After they collided, they became 1 individual object that has now a shared velocity. So the answer is right. I just want to make sure we have the method. So now with that, right, let me get Kimberly and Lakshmi, if you don't mind, would y'all come to the front and get on the board and show your work? Is that okay?
Mhm.
All right. Let me erase it. All right, here you go. You prefer color? Let me just. Let me know if can I see that? Can you see the board?
Yeah.
Oh, okay. I gave y'all C, right?
Yeah.
All right, just talk us through what you came up with.
This is the momentum of the first ball, mass of 10 times velocity of 6, that's 60. The momentum of the other ball is mass of 3 times velocity of 3, that's 9. So total momentum of the balls before the collision is 60 plus 9, which is 69. And then after the collision, they stick together, so it's considered one object. So the mass is 10 plus 3, which is 13. And the velocity is unknown. So it's just V. But we know that total momentum after should be equal to the total momentum before. So that is equal to 69, which we got here. And so B is 69 over 13.
So now, two things, which I seen that you just did at the very end, right? So how did you know to use 69 to find the final velocity?
Because total momentum after collision is equal to total momentum before collision.
Because the total momentum in the system is
Conserved.
conserved. So that's what it really means when we get to the numbers, right? She knew she was able to use 69 because the total momentum in the system is conserved, which means the initial momentum is equal to the final momentum. So she could use that to find the final velocity. Now, also, too, how did you know to add those two masses together for the total momentum afterwards?
Because the picture shows that the two balls are sticking together and going in one direction.
So they stick together, they go in one direction. So what type of collision is that? Inelastic or elastic?
Inelastic.
Inelastic. So now we know the initial look one way, which would be similar, but how we treat it in the after depends on what type of collision we have. So we see them stick together. So now we add the masses because it's inelastic collision. They come together. So those two things are really what you should start off with. Is it an elastic or inelastic collision? And then momentum, you just know momentum's conserved. So momentum's conserved. And then is it inelastic or is it elastic collision? And you go from there. So that's the problem right there. Any questions? All right, good job. Now,
I was just gonna say I really still don't understand the first part.
what's the first part?
Like the before.
What about the before?
Because I couldn't really see the board like that, so I don't really understand how to do it.
We're getting closer. So we're like, what part do you not understand?
Like
Like
the,
about
for-
the
the formula for one.
Don't worry about the formula. Don't focus on the formula. What about the fact of, do you understand momentum?
Yeah, I understand momentum and the impulse, which is the change in momentum. And then it's acceleration or the change in velocity.
Don't worry about the formulas. Momentum. We have two objects, right? The first one is a regular ball that's just going at 6 meters per second. Then we got another ball that's going at 3 meters per second. They both have their mass. And what she did was she calculated their mass times their velocity. Each one, right? Mass times velocity. By doing that, she was able to find their individual momentums and add them together. So once she added them together, she got a total momentum of 69. So once she got that, see you later. So once she got that, she added them together to where now she's able to use that for the second part. Do you get that part right here? Let me stop here. Did you get how she found the individual ones?
So she did 6 times 10 and then 3 times 3.
Yes.
Yeah, I get that part.
Okay. Cool. So now she just did that, right? So now once she did that, she was able to come here and say the total is 69. Because she said earlier that total momentum is conserved. What does that mean? That means my initial momentum is equal to my final momentum, right? Because she did that, now she's able to say this 69 should be equal to 69 in the second part, right? So now she's able to put this over here. And because they stick together, you add the masses together. So you add the masses together to where you get a 13. And then you get this 13. And you could divide that by 69. Let me just make sure I'm slowing down. I'm going to slow down. Add the masses together. And so they stick together. So now that's where you get this 13 from. Because you want to find out what the velocity is, you divide 69 by 13, and you get the final velocity right here. Does that make sense?
So you do. So for the final, for the after, because they're together, they count as one, or because they're colliding,
Yes.
they count as
Correct.
one. You still do 3 plus 10,
Yes.
and then I don't know what do you do with 13. It's just 13.
So now it's 13. Let me just write this in between steps. So now it's 13 times the velocity, which we don't know, is equal to 69. But because you want to find out what the velocity is, you want to divide 13 by each side. So what you do is you divide 69 by 13 to find out what the velocity is, which ends up being about 5.3.
So why do we divide?
Because you multiply this right here. Once you
We
do
can't
that,
see. I can't see. Rather, it's still on the
you see this?
moment. No, I just see like a hand.
You see that?
No,
Just 13.
nope. You're on a momentum problem solving whiteboard, right?
Wait, look at my camera.
Let's see. Oh, I can see.
You see that?
Yeah.
You have 13 times the velocity. So you do 13 and you do divide it, because now this becomes 1. So now it's just the velocity that I'm trying to find. And then you have 69 divided by 13, which is about 5.3.
Okay.
Does that make sense?
Yeah. So do we do because we did multiplication first? Do we do division like this for every problem?
Don't try and generalize it. You see multiplication right here. So to find this variable, you do the opposite. To find this variable, you do the opposite. So you do division because you see multiplication.
Okay.
Is that okay?
Yeah, I get it. Thank
All
you.
right. No problem. All right. I'm going to do A real quick. So this is a momentum problem, right? This is A. So my system is conserved. So what does that mean? The sum total of my initial momentums is equal to the sum of my final momentums. I didn't put the sum earlier when I was talking about it, but this is what I mean when I say this, right? So what does that mean? I got my first mass, and it has its own velocity, right? And I have my second mass, and it has its own velocity because I have two objects, right? Now afterwards, let me see, is this an inelastic collision or elastic collision? I'm gonna look at the picture, right? The picture is telling me that they both stick together. So if they stick together, that means it's inelastic. So this is inelastic, right? With it being inelastic, I know that their masses are going to become joined. So the mass of my first object and my second object are going to join together. With me knowing that now, I have a joint velocity. Let's call it V prime. That's pretty much the velocity that they share at the very end together, right? So now I can start plugging in some numbers. So now I know my first mass, 2 kilograms times 5.2 meters per second. My second mass is 13 kilograms, but I don't see an arrow. It looks like this object is at rest. So I can assume that the velocity is 0. So let me stay on this side real quick. Let me just make this down. This should be about 10.4. And then this would be 0 because 13 times 0 is 0. Now, if I look on my right side, right, because they stick together, I add their masses. So what is the first mass? 2 kilograms. And then the second mass is 13 kilograms for their shear velocity. Now, when I add those together, 13 plus 2 is equal to 15. So I got 15 times the shear velocity. And that's equal to 10.4 kilogram meters per second. Right? Now I want to find out what this velocity is. I see that it's multiplied by 15. So I need to do division so that I can find out what this actual velocity is. So I divide each side by 15 to find out that my shear velocity is about 0.693 meters per second. Obviously, if you're looking online, you can find the answers. It's not hidden from you. But the first part that's important, understanding, 1, my momentum is conserved. 2, what type of collision that we have. Then 3, using the right formula based off of that, and you just plug in the numbers. Momentum is conserved, so my initial is equal to my final. Now it's a collision. What type of collision? They stick together, so now we have inelastic. Because we have inelastic, I know that my masses are being added together and we share a velocity. I should put that in the slide. I'll go add that. Masses share together and a share velocity, right? So we get to the very end here. Any questions on that?
Yeah, I do have a question. When it's not shared,
Hold on.
shared,
What did you just say? What did you just say?
when it's not shared,
When it's not shared. So what type of collision is that?
when it's elastic.
Stay there. Now, we just did these first 3, right? Now, Courtney, look at D, E, and F. What do you see?
They're not shared.
It's not shared. So what type of collision is it?
Elastic.
Stay with me, Courtney. Okay. So let's look at D, right? So now we have a situation where it's not shared, right? So first, we know that momentum is a collision, right? Momentum is still conserved, but this time we see that it's elastic. So now we know it's elastic. Now, what did you just say? It's not what?
Shared.
Shared. So they both do what? They both bounce
Off of each other.
off of each other, right? So now I still have my mass 1. And let's say we got 2 objects, right? I got my mass 1, and that has its velocity. And my mass 2 has this velocity too, right? They have their own individual, and we can find those, right? So the final though, because they maintain their being individual, they bounce off. So now I have my mass 1, but it has a different velocity than before. Let's say final or prime. Then it has my mass 2 has a different velocity afterwards too, right? So now with me knowing that, now I can go ahead and represent these. So let's start plugging in some numbers, right? Looking at D, the mass of the first object is 10. The mass of that, the velocity that goes with that one is 6 in the positive direction. Then we have another mass, which is 3. And that one's going 3 in the positive direction. So let's calculate those momentums first, real quick, before we go any further. So now I got 10 times 6, which is 60. So I got 60 kilometers meters per second. And then I have 3 times 3, which is 9 kilogram meters per second, right? For a total of altogether of 69 kilogram meters per second in my total system. So that's my left side, right? Now over here on my right side, let's look. We have the same mass for the first object, which is, my second object, which is 10 over here, but we don't know its velocity. So that one's unknown. But the first one, 10 is over here. We don't know that one, right? But we do know the second one, which is 3, and it tells us that it's moving forward with a velocity of 9 meters per second, right? So this one we just leave as 10 kilograms times the velocity that we don't know. But we could find this one. It's just 9 times 3. 9 times 3 is 27. 27 kilometers meters per second. Now, I'm going to write it all the way through so we have the units right. But I'm going to just rewrite it so you just see the variables. So we can see the math one more time. So now you got 69 equals 10 times velocity, unknown, plus 27, right? What I'm going to do is to get this to be a one-step equation. Right now, it's a two-step equation. So I see addition, and I want to get rid of this, so I do subtraction. So I'm going to subtract 27 from each side to make this a one-step equation because it's two-step now, right? So this 2, this is 0. This is 4. So this is 42, right? I bring this down. So now I have 42 equals 10 times my variable, right? Now, in between this, once again, is multiplication. Because I see multiplication, I do division. So that's my one step. So I divide here. So now I should get 4.2 meters per second equals my velocity. And it's positive. So which way is it going? To the right. So right here, you see addition by 27. So you do subtraction by 27. Down here, you see multiplication by 10. So you do division by 10. And then once you solve it all the way through, you find out that the final velocity is 4.2 meters per second in the positive direction or to the right. Questions? We good? Hearing no objections, I'll take that as a yes.
Yeah, I think so.
Okay. Now, what I want right now, so you just seen how I did that one, right?
Yeah.
Matter of fact, I'll just do that. I'm gonna put all of y'all into your own breakout room real quick. Or wait, you don't even have to be in your breakout room. Can y'all all hear each other right now? Can you hear them online? Okay, so what I want y'all to do, right? I want y'all to work together to do E and F, right? So Kimberly's gonna come up, she'll be on the board, so she can write as y'all talk. And I want y'all to talk into each other and come up to where you can find the answers for E and F. Now, why I say that is because, Courtney, what do you recognize about D, E, and F?
That they're elastic.
They're all elastic, right? So you should use what? The same
Formula?
just the numbers might change, right? So
Mhm.
try and use the same formula for that you see that we use for D, it's still on the board, and change it around with E and F so that you can find out the values. Now, pay attention to which ones have the missing velocity. So the first one might have the missing velocity in one problem, but then the second one might have the missing velocity. So that means just pay attention to it. But the setup for the problems is the same. I want y'all to use the board up here, like Kimberly write on the board. Y'all can see it visually. Talk her through. You can talk back with them. But I want y'all all three to come up with 2 answers for E and F real quick. Can we do that? Can we do that? All right. I see the thumbs up. All right. You come on down. Yeah, just to the board. And they'll talk you through. And I want y'all to use the board. So like you'll write on the board while like y'all figure out the answer together. And I'm not putting it in the breakout room, so y'all can talk to each other right here. All right. Just discuss. You want to keep this up or you want to erase this?
No, I'm gonna keep it.
All right.
But wait, I'm not getting.
So Kimberly's at the board. She's got the markers, and I'm just sitting back. And we are done. Just let me know. We are ready with an answer for E and F. It doesn't have to be right. I just need y'all to have. You just have to have an answer. And you can use the eraser if you want to.
Do I have to subtract?
So,
The last time I saw him, he was playing. Because the last time. I was dead.
Hello? Hello?
yeah, go ahead. Go ahead, Courtney.
Yeah, that was me. Sorry about that.
No, go ahead. Were you asking a question?
No.
Do you see what Kimberly's doing?
Yeah, I can see what she's doing.
Where you stuck at?
Here.
So what do you see? You see it's a two-step equation.
Yeah, from here, because I was like trying to use this like following.
Mhm.
But for this one, it went the same direction, but for this one, it went like opposite direction. So that means I have to subtract this instead of this one.
Actually, it'll tell you. So you don't know what that one is, right? So you actually leave it, right? But you solve it and it'll tell you. It says it's going this way, but like we want to see, right? So just solve it and it'll let you know. So solve it real quick.
So do I subtract this?
What am I saying? I'm saying something. What do you have on the right? You have 9 plus 2 times 2. Oh, perfect example. Now, actually finish it. Just finish it. Just finish it. Go ahead. Just finish it. Don't worry.
I don't know how to do it.
The last part. You see, and you got now this is just math. So you see addition, right? It's a 2-step. So you got to get rid of that 8 first. So if you see addition, how would you get rid of it?
I mean subtract.
And you do the one side, you do to the.
So it's 5.
Mhm.
And then 3. And then do I is it like this? No.
And you got to make sure you keep the variable with the 3. So it's a v next to that 3.
Yeah.
Yeah. So now what you're doing is you're dividing the 3 so you can just get the v by itself. So now on the next line, right, v is equal to what? What's 5 divided by 3?
One, two, six.
All right. Courtney, Itali, do y'all agree with her?
Yeah,
Okay.
I got that answer.
You got that answer?
I think I just when I was doing it because the arrow on the second ball is facing the other way. I did -2 in the beginning, so I had it didn't do like 9 plus 4, but I did 9 minus 4. We got the same thing. It ended up being 5/3. I was just so yes. same thing.
Wait. Say what you just said. Say what you just said again.
So the ball in like the in the example, the one on the left is like facing towards the right, and the one on the right is facing towards the left. So I did -2 meters per second because it was going the opposite way. So I did 3 kilograms times 3 meters per second. So yeah, 9 kilograms times meters per second. But then that's plus 2 kilograms times -2 meters per second. So it was plus -4, which was
Yeah,
equal to just -4.
So
So
when you said the direction, right? So what
yeah,
part was negative? The 2 what?
the 2 meters per second.
Okay, so now let's think about that. You mentioned that earlier about the one, the arrow's direction, right? So positive, negative do similar direction. So Zelly is right with that point. So now we need to represent the direction of the 2 meters per second being in the opposite direction, which would be negative. So really just put a negative right in front of that 2 meters per second at the very beginning, at the top.
This one?
Yeah, make that one negative. Now, let's keep going from there and see how it differs, right? So now, let's go to the next line. So 3 times 3 is still 9, right? But now that we have 2 and -2, what happens to that 4? Is it positive or -4? -4, so change that. So now with that -4, what do you get on the left side? Is it 9 plus 4 or 9 minus 4? Or 9 plus -4?
Well, 9 minus 4 is the same as 9 plus 9.
So now you have, instead of 13, you have 5 on that side. So now the next line, right? Instead of that 13, put change it to 5. Now let's look at the arrows, right? So the arrows on the other side, right, are pretty much the same, right? You still have 4 going in the right, so that's still positive, right? So we can leave that as it. We do know that 3 is going to the left, but we want to confirm that, right? So we're going to leave that as just 3 times v, right? Now, with it being 3 times v, right, we subtract 8. We still subtract 8, but this time it's 5 minus 8. What is 5 minus 8?
-3.
-3, right?
Can I ask a question?
Go ahead.
Because I got it right up until that point because I did 13 equals 3v1 plus 8. And then I did the minus 8. And then the minus, I'm at 13 minus 8. And I did get 5. But then I took the 5 down. And I divided it by 3.
Now your math is right, right? But what's the key thing that Izeli said earlier? Actually, let me not repeat it. Izeli, what did you say in the very beginning?
So the direction of the ball in the example, one of them has an arrow going to the right. So that's positive, like going forward. And the other one has an arrow going to the left. So that's negative. It's going the opposite direction. So that's why we did -2 meters squared, because it's a negative like velocity. It can't be like a negative mass. But it can't weigh less than 0 in this example. So we did -2 meters per second instead of a positive 2 meters per second.
Okay.
Now we're doing that, right? What Kimberly just did on the board, she kind of just made sure she accounted for that, right? So now instead of it being 2 meters per second positive, it's -2 meters per second, which then makes the momentum of that second ball actually -4. So when you add them together, you have a +9 plus a -4, which really becomes 5. So instead of you having 13 equal to 3 times v plus 8, 3 times v plus 8, you now have 5 equal to 3 times v plus 8. Does that make sense, Courtney?
Oh, I'm sorry. I thought I was off mute. Yeah, that makes perfect sense.
So now stay right there, right? So now we at that point. Now Kimberly did the same thing to where now she has to get rid of the 8 because we want to find out v by itself. So she's dividing 5, sorry, not dividing, subtracting 5 minus 8, which is now what, Kimberly? What is 5 minus 8? So now she got -3, and that's equal to what's left on the right side, which is 3 times v. So write that, -3 is equal to 3 times the v, which is the final velocity. Now you see multiplication, so you must do division. So you divide by 3. Good. So now what is my velocity?
-1.
Yes. -1. That's okay. -1. But now, Kimberly, you said this earlier, right? You said, look at the arrow. It's pointing this way, right? Now, when we did the math, it confirms that it's going in the opposite direction. The math confirms that it's going the opposite direction, and how fast? 1 meters per second. So now the new velocity is -1 meters per second, which means they collide, they bounce off of each other. One goes forward, the other one goes backwards. Does that all make sense?
Yeah.
Okay. Now, what I wanted for this exercise, right? I wanted y'all to work together. What y'all did was y'all individually did it and then came towards the end and talked through it. But you see how I asked, did y'all all get the same answer? And then Zelly came up and said, wait, I got something different because I did something different, blah, 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 blah. That's how I want y'all to do this next problem. I want you to try one more time with F, but I want you to talk to each other about those specifics beforehand so that y'all can all have the same answer afterwards. So look at the direction of the arrows. That determines how you add or subtract. Do it one more time and see if all three of y'all can come to the same answer and just talk to each other through it. You got two people online and you're at the board. And if she's writing something on the board and you can see it, like say something if you don't agree with it, or if you need her to clarify or talk about it.
Okay,
Try that for this last one for F.
I,
Alright,
I
go
did
ahead.
it already.
All right, go ahead. Just talk through it. Just make sure you're just talking. Just talk through it. Go ahead.
Okay, so I did 6 times 3 equals 18. And then I did 4 times 5 equals 20. So then I got the answer equals 38. And then I did equals 10.5 plus 5v 1. And then I scratched out the 10, then I did 10.5 divided by 10.5 and 38 divided by 10.5. Oh yeah, I forgot the part where I did the second bar where I did 3 times, I'm at 3.5 times 3 equals 10.5. That's how I got that. Sorry. And then I did 5v1. And that's how I got those answers. And then the final answer I got was 27.5.
Say it one more time what you got.
27.5.
Okay.
Wait, I think
Keep talking.
so it wouldn't it be 10.5 times, wait, I'm sorry, 10.5, I'm getting a call, sorry, plus the 5.5 times v.
Huh? I don't, maybe my answer is wrong. I don't know.
So
That's
I
good.
was following you up until after 10.5.
Oh no, I did 38 minus 10.5.
Yeah, so you did 38 minus 10.5,
Yeah, I'm
not
sorry. I did
divided
do
by
that.
10.5.
Yeah, I didn't mean to say divide. I did 38 minus 10.5.
Okay, and then that's because I did also get 27.5, but not as my answer. I got that from 38 minus 10.5. So that's
I didn't finish the problem.
and then from 27.5, that would be equal to that 5 kilogram times V you had. So yeah, 0.5 times the 5v1, 5 times v1. Yeah, that's equal to, so 27.5 is equal to 5 times v1, or 5 kilograms times v1. And then we divide that by 5. And we get v1 is equal to 5.5 meters per second.
Oh, okay. I didn't finish the problem.
Okay. Are we saying that's our final answer?
Yeah.
Now, this is what I wanted. The thing is Kimberly took on this scribe and she made sure it was organized to go ahead and put together, right? And she made sure we carefully documented everything that was said, right? Courtney took lead because she already started the problem, right? Now Courtney got to a point to where she actually started doing it right. Like she got to the important part, but she just needed to finish it off. And then Zelly noticed where she was at and was like, wait, we just have to add this one part and we finished it, right? So where we got to our final answer, right? Now, the more important thing, yes, you got the answer 5.5. Yes, it's an elastic collision. Yes, we represented that each of the directions are the right and we set it up right. But the more important thing is you guys work together to put this together and find the answer, right? You looked at it, you seen what was going on, and you really tried to put it together. And you find the right answer at the end. So that's how it works. Everybody has their individual role, but you all come together to be able to solve these problems. Now, think about it, right? You all three of you played a role. Kimberly was writing on the board as scribe. Courtney solved the problem, but then Zelly was kind of like the checking over person, right? Now, when you go by yourself, you might have to do all three of those roles to get rid of solve problem, right? But that's why you have a notebook. I have the printouts for you. That's why you have the notes. That's why we have the answer key. So you can do it, try it out, figure it out, and then you can even check it over on your own to make sure that you did it the right way. When you play all 3 rows by yourself, that's when you really get to learn. So when you go home, think about it like that. Okay, I am by myself, but I have to play all 3 rows. But part of your notes is going to be this recording, what you wrote down in class, what you remember, so that you could try and do this. But this is how the problem solving should be each time. Does that make sense?
Yeah.
All right, so that was good for that one. Now, give me 1 second. Let me see how far we are. Oh, I am taking a while. I want to see if I can finish this, but if not, thank you, Kimberly. Oh, here's the answers. So here are all the answers for the problem here. So you can see how we came about it, but pretty much we did good. Took a little minute, but we got it to get together. All right, so we got this one. Let me just stop sharing for like 2 seconds just to see what we have. Thank you guys for being patient with me.
I don't know how to. I don't know how to request it then. I don't know how to request that. Or maybe I'm tripping.
All right, can you see my screen?
Yeah.
Okay, so let's look, right? Let's do this one real quick. So once we do this one, then we can get to the room. Can you see the board? Or did I need to move it back? Is that better?
I can't see the board. I only see momentum as a conservation guide.
On the what am I talking about?
I see the board.
On the screen. Look at my camera. You can see it?
I can see it.
Okay.
Make sure you just like pinned on, not accidentally pinned on just that one, because you
Okay.
have the slide pinned. Maybe that's why.
Yeah, I got the slide too, like just so you can see the problem. But then, like, I know if I start writing something, I want you to see it on the board too. All right.
So we can't see the board, right?
If you can see it, you could tell me if you can see it.
Hold on. I don't know why it does that. I have to go back to the pen. Oh yeah, I can see it.
All right, okay. So let's do this first one, right? So this one is more so wants you to understand the mass, right? So in each of these, right? Courtney, look at all 4 of these and tell me what type of collision these are.
Inelastic.
Inelastic because why?
They're one.
They're one, right? They're one at the end, right? So what I know, right? And these are a special case, right? These
Right.
are an elastic collision where the first object is moving, but what do we see about the second object?
We don't know. It's together. It's inelastic.
Afterwards, right? But look at the before, right? So tell me what's going on with A. A is doing what? It's moving in what direction?
A is running into B.
Running into B.
Colliding with
But what does it say above B?
rest. B is rest.
What does it say in the next one above B?
It's unknown.
What about the next one in B?
Oh, I'm all the way on A. If we're on B, it'll be together.
Sorry. In A, look at the before. B, it says it's at what?
It's rest.
And at B, and B, the next one, right? Look at the before. The object B is what?
It's unknown, so it'll be 0.
No, object B.
There's question marks on top of it, right?
Object B.
Oh, the 6.
No, object B. Before.
It's at rest.
Rest. Look at C and then look at object B. One more time at before.
It's still at rest.
Same thing for D, right?
Yeah.
So what we see is a situation where the first object is hitting an object at rest, right? So then we want to see what their velocity is when they join together, right? So this is more logic than it is math. So first things first. In my system, momentum is conserved, right? We established that it's an inelastic collision. So now when it being inelastic collision, we know that the first mass has its velocity, and that's equal plus the second mass and its velocity. But when we add them together, when we see the collision afterwards, the masses should be added together and they have a joint velocity, right? Now, what do we know about this one? In this situation right here, right? Each mass of the second object, each second object is at rest. So its velocity technically is 0. So what does that mean for our equation, right? This is actually in each situation. That means that this whole term, all of this becomes 0. So now I'm left with mass 1 and its initial velocity is equal to mass 1 plus mass 2 over its final velocity, right? Let's do final here. So, hold on one moment. Sorry. So now we're here, right? My fault. Then now we're here, right? We have our mass now of the first object, and its velocity is going to be equal to their joint masses together with this velocity, right? So we can see how this comes out and now be able to represent the change in the velocities, right? So now we want to see the factor of the original value. We don't really want to know the actual value. We just want to find a representation of it. What do I mean by that, right? If A is our first mass, right? What is that first mass? Right here it says 2. So I can just plug in these numbers, right? And then I have that times 5. And then our masses I add together, right? So now I know that if I add these together, I have 5 plus 2, which equals the initial velocity, right? So now I have 7. I think I'm doing something wrong. Hold on. No, it's 3.5. Sorry. 2 plus 3.5. Yes. So now I have 3.5. So that's 5.5 times, I think it's, just give me a second. 5.5. Yes. Let's do it like this, like we don't know what this value is. So now we want to find what this is. So this is 2 over V, right? I don't want to confuse like the initial. Equals 5.5 over this new value. To figure this out, I would just divide this by this. So now I get basically, if I make it a nice fraction, this is what the answer is going to say. 4 over 11 times V equals V bar, right? All I did was just kind of just switch it to where I just found the value, the math for it, but we're really just trying to find a ratio of it. Now, what can I do, right? I can just go ahead and plug in 5 right here and find that value because they actually tell you what this value of this one is 5. So you would do 4 times 5 over 11 equals this. So you get 20 over 11 equals V1, right? But this part's not the most important part. This part is finding a relationship. Now, let's just do this together so we can run through it because this might get a little confusing, right? In
Yeah,
each
it is.
it's one, momentum's conserved, and it's elastic. Now we got to do is just fill in the blanks. Oh, and for these ones, it's at rest. So we can literally go 1, 2, 3. We could start from here each time to where now we're on this part of the equation. So all we got to do is change some things around, right? So go to B. Courtney, you see question marks. Where do you see question marks?
Over. Because I was right on the back of it. You said go to B.
Yeah,
It's
where do you
over
see question marks?
over B.
On B.
Over A.
Over A. So we don't know what this value is, but we can leave it. But we know the mass. So I'm changing the mass. This is B now. This is 4.8. So now I can come over here. What is the mass of A? 4.8. What's the mass of B? 3.2. Right? I'm going to leave it, right? So now we know that here, this is 4.8. So I'm going to change this to 4.8. This is 4.8 plus 3.2. This is 8. So now I could do 4.8 over 8. I'm going to make this nice. 4.8 over 8 actually ends up being 3 over 5. If you doing your calculator, write down 4.8 divided by 8 and tell me if it's 0.6. 4.8 divided by 8. It should be 0.6. Okay, 0.6 is 3 over 5. So I'm going to write 3 over 5 times V1 right here. So that's the relationship. So we're just trying to find this relationship, right? So we got that. This is 3 over 5 times the initial velocity, which means that the final velocity is 3/5 of the initial velocity. That's all we're trying to find is this. We can plug in 6 over here and then solve for, but we don't have to do that. This might be a little confusing, so go back and rewatch this after we do this, but let's just do the next two together. One more time. We know this is true, so this is the third one. 1, 2, 3. It's the same thing. So where can we start from? Right here. Courtney, on C, where do you see question marks at?
Over under A. For the
Under A.
mass.
Don't know what this is. Where else do you see question marks?
I see it. I see it for the mass. For A.
For A?
The 4 on C, right?
Yeah.
This M question marks under the A.
Mm-hmm. So now we know that the second one, right? It's at rest, so it's still 0. We don't know mass 1, but we do know mass 2. So we can represent this as M plus 1 over this, right? And just there's an M, right? Now let me just move this to the side. We don't know all of this, right? Just give me a second. So we know that this one actually is, we don't know this, but we know this is 6, right? And this actually changes to 6 over 8. So what I can do is represent this over here as 6M equals M times 1 times 6, right? Sorry, 4.8. Now what I'm just trying to do is find the factor, right? So if I divide by 4.8 here, oh wait, let me do 6, yeah. 6 over, because I want to find out what M is, over M plus 1. So now you have 4.8, so that's 8 over 10, right? So now if I come here and one more time, trying to figure out how I would do it. Hold on. Yep. So then we get here, right? This is just some math, right? 2 over 10. I'm just rushing through this. I'm not going to lie to you. So now we get M divided by 2 over 10. These 10s cancel out to where we get M equals to 4. But really, it starts off with just establishing this part right here. You get M equals 4 equal here, right? They want you to find that one, and they want you to do the same thing over here. But let's go through one more, because I'm just going to finish this, but I'm not going to spend too much time on this because this is proportional reasoning. But really, one more time. We go here, here, here. It's the same scenario, right? But this time we don't know the mass again, right? So now we just do the same thing. We don't know the mass, but we do know that this one is 2. So now we know this is 2, and we know that the speeds, the velocity, this is 9. This is 7.5. Once I get here, I could do 7.5 here. Then I can get 9 here. So now I do 9. I did 9 here. Once I make it nice and pretty, this ends up being what? 5/6. Yeah, 5/6. So now you can switch this up. If I multiply this through, I got this is 6/6. This is 5/6 plus 5/6. So then if I subtract, now I got 1/6. And then on this side, I have m times 5/6. Then if I divide by 1/6, the 6's cancel out. So I got m is equal to 5. Now, all of this is just math. I recorded it. You can go back and look at it. But what's the most important part for this problem? Understanding my momentum is conserved. It's an inelastic collision. And now that there is that rest, this is our new equation to represent the situation. From here, you can take out any parts of it to figure out the missing parts. But just these 3 parts. Conservation of momentum, inelastic collision, and then understanding when the object is at rest, now you create the proportional. This is really just to help you just think about it, but the goal was not to get you to be confused with the math. I know I just rushed through this part. Bear with me. Don't focus too much on this, because if you got to this point and it made sense what Courtney was saying earlier, like the difference between when they bounce off, it's elastic. When they stick together, it's elastic. That is the most important part. If you got that, you're good. This is just to help you out. Don't get stuck on this. Now, this right here, we are at the end. This is the last problem. As you see the answers, I'm not even going to spend too much time on these answers. This is not that important. This is the important part. This is the problem that's on your final exam. This is the one that's on your final exam. This problem right here, right? We have a bowling ball moving east at 2.4 meters per second. It strikes a stationary 90.95 kilogram bowling ball pin. Immediately after the head-on collision, the pin is moving east at 5.19. Determine the post velocity of the bowling ball, right? So let's put this all together. Everything that we've done to this point so far is just coming to solve this one final problem. So let me draw a picture. I got my bowling ball. It's rolling. So where it hits this pin, right? This is before. The bowling ball is moving east. This way to the right. The pin is at rest because it's stationary. Not moving, right? Now afterwards, now the pin is moving east. And the bowling ball is going either forward or backwards. We don't know. So we have to figure it out. Which way is the bowling ball going? The pin is going east. How fast is the bowling ball going? East, 2.4 meters per second. The pin is at rest, 0 meters per second. And then when the pin is moving east, it's going east 1.9 meters per second, east. So if we look at what our unknown is, what is the final velocity of the bowling ball? We don't know that, right? What were we given? The mass of the bowling ball and the mass of the pin. So we have two masses, right? And we have initial velocity of the bowling ball, right? And technically we assume that the initial velocity of the pin is equal to 0 because it's at rest. So with all of these, we can look at these and see what happens.
I think his computer probably died.
Did we wait?
Almost done. No, it just went out on me. They want me to be great. All right. Last one. We just said it's elastic, right? So now we know that momentum is conserved. The individual momentums, we got the bowling ball and its velocity, right? Plus the pin and its velocity. In the initial, it's this, right? But in the final, they also have their individual and they stay together. Sorry, they individual, they're separate. So you got the bowling ball afterwards, and you have the pin afterwards, right? And if we go back, we want to find the final velocity of the bowling ball. So really the one that we don't have is this one. We don't know. No, sorry. This one. We want to find this one. But technically, we have all the other ones, right? Let's see. I can change this. Let me make sure I highlight which we're trying to find. We're trying to find this, but we have everything else. This mass was given to us. What was this mass? 288, right? No, 488. This mass is 488. This speed velocity was given to us too, right? What is it? 2.4, 1. This mass, we have it right here. What is it? 0.95. But we also said that it was at rest. So this velocity we assume was to be 0. So this is 0, right? This mass is still, let me start with this. So now this is 0. This is 4.8 times 2.4. That should be 11.76 plus 0, right? Now, if I come over here, right? Actually, let me just do this all together. So now we got 11.76 kilogram meters per second for my total initial. Now, once we come over here, right? We know that this mass is 4.8 for the ball, but we don't know this value. So I'm gonna leave it in green because that's the one we want to find. We still want to find that one. But do we know this mass? This is just for the pin, which is the same one right here. 0.95 kilograms. And then they tell us the speed that it comes out with the pin afterwards. 5.9. 5.19. So all I got to do is put those together and multiply. So then when I multiply those, I should get 4.9. So I get plus 4.93 kilogram meters per second equals to 4.8 kilograms times the unknown. Now let me write that all clean one more time here. 4.8 plus 3.9 and times is V. Now this part right here is just the math. I see down here, I see addition. I need to get rid of it. So I see addition by 4.93. So I subtract by 4.93. So I'm going to subtract 4.93 minus 4.93, and I should get 6.83. So now I get 6.83 is equal to 4.8 times the final velocity. Now I see multiplication by 4.88. So I want to divide by 4.88. So now I divide by 4.88. And I should get my final velocity, which should be, did you get 1.4? Do 6.83 divided by 4.88. $1.4. I got through this. We are done with this unit. For this problem, which is the summary of all of this, momentum is your mass times your velocity, right? Objects have momentum when they're going moving. Things that change momentum are forces, right? A force over time, an impulse, right? Can affect it, right? But when we look at that, right, in a total system, your momentum is conserved. So by doing that, we can look at collisions and figure out what individual quantities are after a collision. So whatever your momentum is before a collision is the same after a collision in a system. So doing that, we can evaluate between elastic and inelastic collisions where we have objects that bounce off, maintain their individual separate momentums, or objects that join together and actually fuse and have a similar mass together and a shared velocity. And by doing that, we can framework a system of equations with the mathematics, so where now we can find these individual quantities. Physics, 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 now math. If you can get to this point up here and understand this, this is just basic math afterwards. But these three concepts really are the whole break of this entire unit. But this is the final problem that we need to know for the final exam. So make sure you go back and use this. It's also the first problem on the practice exam. But we are done with momentum. And on Wednesday, we'll be starting energy. So let's wrap this up. Thank you for being patient with me. If you're watching online or you're watching later, come with questions. I'll make sure this is up before Wednesday's class so we go through it. But that is it for this unit. Any questions online?
Oh, my brains are fried.
Say it again.
He said our brains are fried.
I know. I just had to get through this, but I'll put the recording up there, and then I'll make sure I answer any more questions if you guys have any, because I know I kind of got rushed through this, but I try to do the best to make sure we can stay on track. Just play around with the problems, and if you have any questions, they'll be due from a week from today, this one, because we just finished it today. So you got a whole week to go through and finish this one. So if you have questions, just email me. All right?
All right. Thank you.
All right. Have a good night.
Thank you, you too.
No problem.